I took 2 hours basically almost to reach so the topic was really insane. So it's surprising that on Sunday. Morning.
Hi, you can use that to change the slide. Hello?
Yeah.
Yeah, you can use that logic device to change the slides.
Which one?
Yeah, next. The one you just put. Yeah, correct that one.
It doesn't work.
Yeah, it worked. Just click on slide once.
Okay. With the finger?
It's not touchscreen. It's not touchscreen.
Use the keypad. Using the keypad.
The keeper? The keeper.
Start.
Oh, great. Thanks.
Yeah, arriving. Trains are on strike.
Oh, yeah? Well,
That's
yeah.
always pleasant.
Well, yesterday it took quite a lot of time actually to arrive here, so traffic was horrible.
Oh, okay.
So it was surprising because on Sunday I didn't expect that.
Yeah, that's right.
But it was just like any other normal day.
Yeah. Right. So what is your hotel? It's nearby?
Yeah, well, it's kind of 10 minutes up
Oh,
or whatever. But yeah, no, it's close to here. But even to reach there, so it was. Yeah, well, one of these times.
Yeah, these were the yesterday because when we were having
Oh, yeah, but
yeah.
5 minutes left.
Welcome everyone. Today's first talk will be Rudy, also all the way from Barcelona, and he'll talk about some determinantal models.
Thank you. I was waiting for this recording is just starting or something. Well, it's okay. So, well, first I would like to. Okay, so well, first I would like to thank the organizers for inviting me to give this talk, and well, all of you for coming. So I will try to explain. Well, the title probably will be. Yeah. Well, the idea is somehow to explain the contribution, or my contribution to what I'm going to be explaining here is based on a preprint that is on the archive with Mateo Levi and Joaquim Ortega Cerdá, myself. Both also from Barcelona. And well, my first goal will be somehow to explain a little bit all these notions that appear in the text. So, well, I will be basically studying, in fact, asymptotic fluctuations of linear statistics, and well, I will first explain a little bit. Well, I guess maybe I hope it's work, but well, in any case, I will mention some results and things, and all of this can be found in this paper. Okay, so, but well, apart from that, if you have any question at any point, I will have questions. Well, the first thing I would like to explain is, or to define somehow. Well, I'm not going to be very formal, but is the notion of a point process. And for this, well, I just basically start with some examples. Okay, and the first one will be this maybe now it's better. It's given by this well, the zeros of some random polynomials. Okay, so we have this. Well, there are different names for this kind of polynomial. So you have this sums of some. Well, you have some deterministic coefficients, the variable, and you have these HJs, which are identically distributed and independent normal complex random variables. And so for each realization, let's say, of all these random variables, you have a specific polynomial. You can compute the roots. And they will live in the plane. But well, the nice thing of these polynomials is that if you move the roots to the stereographic projection, well, they end up in the sphere very well distributed. And well, this was actually the reason. Well, this picture is actually from a paper by Beltrán and Schuh, and this was basically the reason why in this paper, for example, they show, or they are able to show, that these random zeros are actually what they have low, let's say, or good logarithmic energy. Okay. Well, in any case, the idea is that given, so there's some background probability space, and then for each realization, I have some random set of points. Okay. So, but well, another example. So I will. These examples are going to be in the sphere. So the second example can be, for example, let's a simpler one. So you can consider this binomial process. So you can just choose a number of points and consider a uniform distribution on the sphere. You can pick any points, any number of points, and And well, you will get some picture like this. And well, another sort of related famous point process is this Poisson point process when the number of points are not fixed. And well, basically, I guess the difference is that you start first sampling through a Poisson random variable the number of points, and then you can use this binomial to get the grid realization. Okay. Well, this is just another example. Okay. So given there's a probability space, and you have some discrete set of points, random set of points. And finally, another point process in the sphere, this spherical ensemble. So if you consider now independent n times n random matrices with random variables as entries, well, you can compute the eigenvalues, and well, it turns out that again, if you map this, this is a point process in the plane, but if you map these points again through the stereographic projection, well, you end up being nicely distributed on the sphere. And in fact, well, I don't know if it's really clear from the pictures, but there's a, let's say, difference. That's the third, right? Yeah. So this is the, let's say, binomial, and you see that you have more holes and then you have clumping somehow. But here the points are much better in terms of distribution, formal kind of distribution. Well, these are just examples, but this is somehow the idea. I don't really want to go to the formal definition of all the things, but I guess I will have to on this write something. So so here I have the definition of a point process. I will be working basically in RD or in the sphere SD. And well, this is the idea. So we have a metric space if you want, and some probability space, and a point process is a measurable map from this probability space to a space of measures. So we can for each omega in omega we get a measure, and so we get a countable sum of the measures. Well, the idea is, well, here the notation is somehow so I will denote basically. So if I consider a point, an omega here in this probability space, then well, for a, so I have my domain E, if you want, the sphere, and for each omega, this is my point process is going to be like this. No? So I have this C or X omega, and this is now a measure, discrete measure in this set E. Okay. So well, in particular, if I consider some fixed Borel set, if you want, in this metric space, then this is going to be a random variable. Yeah? So for each omega, and this is going, well, it's going to be the random variable counting the number of points of my point process in the set C. Okay. So for each omega, so in this previous examples, I have I have some fixed number of points here. Okay. But if I consider a region, then I can have my random variable counting the number of points in that region. Okay. So for each omega, I will get a given number of points. Okay. Well, in fact, I'm going to be considering what's called simple point processes. So point processes such that well, this probability in the background assigns most measure 1 to singleton. So there are no multiplicities if you want in the points. Okay? And well, in this sense, then you can basically consider that point process can be identified with just a random discrete subset of points in my metric space E. Okay, so this is essentially just the idea. Okay, well, but this random object will be determined by a distribution, and well, this is the, let's say, formal definition of the distribution. But well, the idea is that so this will be now a probability in the space of measures. Okay, so this is going to be now the distribution of this point process. And well, this distribution can be characterized in different ways. But well, here you have some of them. But I will basically, because it's more useful, consider a particular way to characterize the point processes that I'm going to study using joint intensities. Okay? So I will define now this notion of joint intensity. And here is the definition. Okay? So if we have a simple point process as before, so and we have a measure in my metric space, okay, mu, then if there exists some functions like this, so we have a function from this Cartesian product of E to a positive or non-negative function, and such that the expectation of this number of point products of number of points in different sets, C1 to Ck, the joint sets in E. If this is given by this integral, this will be the joint intensities. Okay? In all the cases I'm going to consider, this is going to be the case. So this joint intensities exist, and I will give you a particular expression of this. Okay, but well, the point is that this is a very convenient way to define or to determine these point processes, and well, by the way, if I have to recommend a reference for all this point processes subject, let's say, so I will right here is the book by Ben Paul. Day4. It is, and yeah, it's called zeros of Gaussian analytic functions. Well, this is
With respect to the measure, I understood the definition of.
well, I mean, well, here you have a measure. So if you want in the sphere, you have just a Levitt measure, the surface Levitt measure, and then well, the distribution can be determined in terms of some integrals, and this is going to be integrated. So
How is this measure appearing in the previous definition of the simple point process that you used? Previous.
no, was before.
It's just one slide before I. Okay, so here.
There's no mu.
Oh, I see. So I understand.
No, I mean, this is if you have this, then you can define to this integrals with respect to that measure the distribution. Okay, so
the row case characterize the point process.
sorry.
The row case characterize the point process always.
Yeah, if they exist under some conditions, I think yeah, but all these conditions are going to be met in our case. So, but
Okay.
yeah. And okay, for all these technicalities, let's say, you can check functions and determinantal point processes. 2000. So, well, in particular, well, I'm an analyst, and as an analyst, I mean, this is really an excellent book to start with this. Okay. Well, okay. So, but once we have this, so let's assume we have a point process, and it's given by it's determined by the distribution is determined by this joint intensities. Then why is this useful? Well, for example, we can do the following. So we consider this. And now I will define another notion appearing in the title. Okay, so now we have at least an intuitive idea with this point process, and now I will define linear statistic. Okay, so well, if we consider in this formula just one set, okay, so we consider some set C, then we are going to be able to measure in terms of some integral the expected number of points in this set. Okay, call that this is the random variable number of points in C. Okay, and so C is just a Borel set if you want in my spherical form. So, and this is well, just by this is the integral of this function rho1. Okay, and well, in fact, now if you consider well, first simple functions and then non-negative measurable functions, and you approximate an increasing sequence any positive non-negative measurable function or integrable function, you can actually extend this formula to compute the expected value of this quantity here. Okay, so well, the idea is that I have these exercises are the realization of my point process. Okay, so these are, if you want, random points. Okay, the random points in E, and then here I have the sum of the evaluation of this function in these points. Okay? So in particular, if I consider as phi the characteristic function of C, I will recover this. Okay? So a particular example, this, and so this is an extension. Sometimes it's called Campbell formula. This one. Okay? And well, in fact, this object here is what is called a linear statistic. So, okay, so it's just basically, so we have this point process, and now we consider sums of evaluations of some fixed function. Okay, and using this device, this joint intensities, we are able to compute the expectations. Okay. Okay. And well, just well, as example, so I don't know. Well, yeah, you have, for example, you can compute things like the number of points, but you can also, for example, if you're on the sphere, you can at least component-wise, you can consider the expected center of mass, for example, of a group of points. So you can measure different quantities that may be of interest in the study of this random point process. Okay. But well, these are point processes in general. But I'm going to be considering just a particular class or subclass of point processes, which are these determinantal point processes. Okay? So now I'm going to define this notion. And I will basically use this. So there are different ways to do it, but when good one, let's say, will be to use this joint intensity. So if they have a particular structure, in fact, you have this. Yeah. So if I consider now a point process, yeah, this X point process. So this is going to be now a determinantal point process if there exists a kernel function. So a function from the product E times C value function if you want, such that the joint intensities, okay, are given by determinants of evaluations of this kernel. Okay. So this is the definition. Okay, so if my point process is such that these joint intensities that if they exist that determine the process are given in this way, then it's a determinant of point process. Okay, well, it may look very artificial, but we are going to see that in fact there are nice examples and of these objects. Okay. Well, this determinantal point processes were this defined in generality in this way, let's say, by Mackey in the 70s, and they were called, I think, at the beginning, fermion processes, because somehow the idea was that she wanted to model somehow the behavior of fermions, so particles that satisfy the Pauli exclusion principle, so they have some repulsion between them, and this is somehow a way to do this because, well, if you think about it, so if you have 2 points here, something that probably is useful. So if you consider this joint intensities, you can these are somehow like densities, okay? And now if you consider 2 points which are very close, now the determinant will have two columns that are, or two rows that are going to be very close to each other, and then this is going to be close to 0. Okay, so the intensity, the probability of having points there is going to be small. Okay? So there's some repulsion built in the definition somehow. Okay, using this, and well, they were somehow, I guess, I don't know, forgotten maybe or something at that time, and then they returned after some years. Okay, so this first definition of Mackey in the 70s, you'll see that well, the main results or that I'm going to mention are from much later. But well, the point is that you have this notion of determinantal point process, and well, something that is also worth mentioning is that they were examples of these processes known much earlier than this definition. Okay, so this was the general definition, general framework of this, but they were known from before. You'll see that there are very.
So the determinant is a measure for the repulsion.
Yeah, because well, I mean, if you have 2 points that are very close,
Yeah.
so if you write this determinant,
Yes.
then this you have 2 columns.
Yeah.
So imagine that you have the same point twice. So you have exactly two columns equal. Then the determinant will be 0. So there you have a small probability of having
points.
or having points.
Oh, okay.
So this is somehow.
Yeah. So it's kind of the inverse. I mean, it's.
Yeah.
Yeah.
Yeah. But well, the point is that these sort of processes appear naturally, for example, in random matrices, or you could say statistical mechanics, or even in number theory. Well, I'm not going to mention any of this, but well, this the reason why they now are lots and lots of information about this. Okay? But well, once we have this object, so we have this point process given in this way. Okay? So let's. Well, by the way, from those first examples we saw, basically just the last one is determinant. So this is very common sample is actually determinant. Okay, and it's possible with a kernel to build a kernel such that the join intensity functions are given by determined. Okay. So these others are not determined. Okay. Okay, and but now I would like to somehow be even more specific and consider a particular well, because
What all would be determinantal if you take K?
well, that's a degenerate. Yeah, it can be considered. This Poisson point process can be considered also a degenerate case or limiting case of point process also. Yeah, but yeah, yeah, thanks. Okay. But well, something that I will need basically is to know what do I need in the kernel in order to be able to say that I have a determinant point process. Okay? And this was actually solved by well, as you can see here, it's a gap. Okay? So the both this. And the idea is that well, you have well, this is technicalities. So I'm not going to go into this, but I mean, well, it's just to have some formal definitions. Okay, so yeah, if well, you can consider a kernel function and define the corresponding integral operator with that kernel. And if this integral operator is self-adjoint in this space and is locally first class, then the kernel defines a determinant point process if and only if the spectrum of this integral operator is in 0, 1. Okay. So I mean, for example, the fact that the eigenvalues should be bigger at least than 0 is also because I mean, if not, this object here is not going to be positive or non-negative. Okay, so there are some requirements that follow from what I need for this joint intensities, and but they are somehow encoded in this. Okay. But well, in fact, I'm going to talk basically about a particular class of determinant point processes, which are called projection type. Okay? And on this point processes, in fact, all the values are 1. Okay? This may look a bit too concrete, but well, the fact is that most of these nice examples are of this type. Okay, so this, okay, but even more so. Well, the point is that what's the interest for me at least as an analyst is that the kernels appearing are going to be, well, in all the cases I'm going to discuss, are going to be reproducing kernels of some Hilbert space of functions. Okay, so I will recall what's this thing here. So reproducing kernel Hilbert space, reproducing kernel Hilbert space is Hilbert space. So we have a Hilbert space of Hilbert space H with some scalar product like this. And well, it's a space of continuous functions. Okay, so this continuous H space of let's say continuous functions defined in some set. Okay, so define some set, I don't know, D. So you have functions from D to C if you want, and this is let's assume this is a Hilbert space. Okay. Then this is a Hilbert space of this type if there exists. So formally, let's say, so if for all points x in D, there exists a function, let's say k sub x in my Hilbert space, such that for all functions in the space, even for this one, the scalar product of the function times the kernel is the evaluation of the function. Okay, so it's just basically that you have a specific and unique function actually in your space. That is so nice that if you want to the evaluation of any function at the point, all you have to do is to consider the scalar product with that. Okay. So well, there are some conditions. So this is not true in general. Not always this is possible. But I mean, for example, if point evaluations are bounded, then this kernel function actually exists. Okay? But in other cases, it's even more simple because yeah.
I'm a little bit irritated by this, that you say this is a space of continuous functions. I mean, you don't want to have like a two or what?
Yeah, no, I'm saying that, well, because I'm considering here evaluations. So if I consider L2, so this is not clear what, so in a point, it's, so I need to be able to say I can evaluate the function. So at least I will assume continue. But I'm not going to talk about the reproducing kernel spaces in general. Okay? So, but at least you need some way to define evaluation. So you cannot consider L2.
Okay.
But a particular example, I don't know. This you can take. The space of trigonometric polynomials. Okay, so if you consider Pn trigonometric polynomials of degree at most n, this is a space of finite dimensional space, dimension 2n plus 1. And well, you can consider, for example, the scalar product given by well, by the L2 norm actually. Okay. So you can consider P hence Q. Okay. So this is a scalar product, and well, this is a Hilbert space, and well, it's very easy to well, these two convince.
So you always consider finite dimensional space?
No. But I'm just giving a particular example. Okay? So this is in this case, I mean this subject exists because you can actually solve a matrix. Okay? So it's not you don't require machinery to define the kernel. But the kernel, in fact, is well known. So the reproducing kernel is actually the Dirichlet function. Okay? The Dirichlet kernel. So you consider this Dirichlet kernel, so the sign of n plus 1/2 theta minus theta prime divided by the sign of theta minus theta prime divided by 2. So the Dirichlet kernel, this is actually the reproducing kernel. So you can actually check that if you consider any polynomial, you take the scalar product, you get the evaluation. Okay? But there are other examples, of course, I don't know. So in fact, in Janir's talk, he mentioned this Bergman space and the reproducing kernel, the Bergman kernel. So, or you have also, I don't know, the Hardy spaces. So you have different, I will mention some examples, but yeah, you have finite dimensional or infinite dimensional kernels or infinite dimensional spaces. Okay. And both can be in this class of reproducing kernel Hilbert spaces, but you need a way to evaluate functions. Yeah.
My question is trigonometric polynomials means the space generated polynomials of sine and cos. Is that?
The what?
The space.
Yeah. Well, it's the space. Yeah. The span of the space of yeah.
Of sine.
Space of polynomials of this of degree at most.
Okay.
Well, this is just an example, but But well, in fact, all the kernels that I'm going to work with are of this type. Okay? Well, in some sense, all of them can be like this because you can somehow build this particular space. But well, there are going to be kernels of well-known spaces. Okay. So, but so now we have this already different notions of list of appearing in the title, and I will now define another one. So the idea of fluctuation. Okay? So what I mean by a fluctuation. So so we know what linear statistic is, and by a fluctuation, I mean just the variance. Okay? So call it just the variance. So the fluctuation of a linear statistic of the determinant of point process has a particularly nice expression, actually. Okay? So let's see. Well, we know that in this for these determinantal point processes, the joint intensities are given by determinants, and well, in the particular case of the first intensity, well, this is just the determinant of the evaluation in a point, and this is just the kernel in the diagonal. Yeah? So this row 1 is just the kxx. Okay? You have just one point. The determinant is, let's say, trivial. When you consider row 2, you have already something. So if the row 2 is joint intensity for the 2, let's say, is by definition the determinant of kxx, kxy, kyx, kyy. Well, if you compute this, you get this expression here. So you have a particular expression in terms of the kernel for this second intensity. And well, the objects I was mentioning before, so the linear statistics that I'm going to write like this. So the sum of the evaluation of a given function f in these random points, okay, this linear statistic, the expectation of this random variable can be computed, we know, using this Campbell formula, like the integral of row 1. But if I'm in a determinant point process, then row 1 turns out to be just this kernel in the diagonal. So this will be the expression. Okay, so the expected, if you want, number of points will be just the integral with respect to so the integral in the so if you consider here the number of points, it will be the characteristic function, and it will be the integral in the set. Okay. Okay, so this is, but if I talk about fluctuations, I will need an expression for the variance. Okay, and in the case of the variance, well, it's possible to show. I'm not going to do it. It's an exercise if you want. That in fact the variance is of this form. Okay, so it involves. So by definition, it involves row 2. Okay. But in fact, well, if you compute, you will end up with this expression. Okay, so and I will be basically starting from this point. Okay, so this formula is going to be important in the rest. Okay? Well, just before the example, so to finish with this introduction of general notions about determinant point processes and all this, I will mention a final result. It is this central lead theorem, so proved by Shostakov. So if you have now a family of determinant point processes, well, suppose that you have some hypothesis on the function, then if the variance grows with this increasing or with this family of determinant of processes, and it says that the expectation of this linear state is controlled by the power of the variance, then he proved that that in fact you have asymptotic normality. Okay? So this expression converts to a normal. Okay, well, I don't know if I'm going to be able to say much about this, but well, there's a general result about a central limit theorem for these objects. Okay, so okay, and you can see here that well, in order to apply this, all you need basically is to be able to control the variance. Okay, this is always easy to compute. But well, you have to be sure that if you apply this, you have to know that the variance grows and that it grows more than this. Yeah. Okay. And now, well, any questions or comments?
So the underlying measure can be recovered from the kernel is like the x-axis.
You mean in this? In this?
In this, if you just give me the kernel, can I like it's something like kxx, the density of the underlying measure or something?
Just not in general. Yeah.
So is it like the kernel contains kind of at least theoretically all the information about the
About the space? Yeah.
no about the process?
Well, I mean.
I'm not talking about
Yeah, but the process, yeah, completely, yeah. So I mean, the kernel determines completely because it determines the joint intensities. Okay. So it determines
and
the
also
process.
the underlying measure. Actually.
Well, but the underlying measure will be somehow here. So because this scalar product is with respect to well, because in all the cases I'm going to consider, this is scalar product with respect to the measure. So this. Yeah. So you have different sorts of objects here, but well, they are somehow related. But well, there's a specific metric related with this, so the metric kernel. But I don't think that you can do the measure from that. I will have to think about it. Okay, well, I will give you now examples. Okay, the examples that I'm going to work with. Okay. And well, the first is basically a generalization or yeah of this trigonometric polynomials. Okay. And the corresponding point process, because well once you have a reproducing kernel Hilbert space like this one, you can define the joint intensities given by the kernel, and this is now a point process. Okay. So the point process corresponding to this generalization is going to be the harmonic ensemble, and this is why I'm writing this thing here. But first, I will just define objects on the sphere. Okay, this is not random. So the objects are the following. So if you consider the sphere, well, you can well, following this, you can consider the space of polynomials, well, in d plus 1 variables of degree at most L, total degree at most L. Well, if you restrict this these polynomials to the sphere, you get a space of functions. Okay, and well, I will write the dimension of this space as small pi L, and well, it's just to see that this is of order L to the d pi. In this case, this is 2L plus 1. No? And this is 1, but it's of order L. Okay. Well, it's possible to see. I'm not going to prove it, but it's possible to see actually that this restriction of polynomials to the sphere can be written in this way: is the sum of the sum of the spherical harmonics of a fixed degree. Okay. So what's spherical harmonic? So these are the eigenfunctions of the Laplace-Beltrami operator in the sphere. Okay. So here you have two different things. One is the space of spherical harmonics, if you want. So this is eigenvectors of eigenfunctions of the Laplace Beltrami. You have the span of this on the sphere, and this is giving you a space. But it turns out that this is exactly the same as just considering polynomials and restrict to the sphere. Okay. Well, the nice thing with this is that, well, as is well known in this case, well, this is a generalization of, well, you can generalize this Fourier analysis if you want to the sphere with this spherical harmonics. And well, L2 is the sum of all these HLs, this space of a spherical harmonics of degree exactly L. And now you have a Fourier series expansion. If you want, you have a function in L2. You have this composition of the function in L2 of this in terms of this Fourier series. Okay, so you have a Fourier analysis if you want in the sphere. Okay, by now it's just that we have this space of polynomials and we have this Fourier analysis. And well, it's possible to compute actually. Again, well, this is again a finite dimensional space, and it has a reproducing kernel, and it's not so difficult to show that actually the reproducing kernel is this object here. Okay. Well, I choose some normalizations. So if you consider, so this thing appearing here are these are the Jacobi polynomials normalized in a particular way. So these are polynomials in 0, 1, with respect to some weights. But well, normalizing these polynomials in a certain way to satisfy this. This scalar product is just the scalar product of 2 points on the sphere. Okay. So the geodesic distance, if you want, is the geodesic distance of the sphere. It's just the arc cosine of the scalar product. Okay. So if you want, you can write also this in terms of a function evaluated on the distance between points. But well, the point is that now that I have a kernel, I will define the harmonic ensemble, and this is now a point process. Okay, so I will define a point process on the sphere using this kernel. Okay, so by this I mean I will consider that these joint intensities are given determinants of this particular kernel. Yeah.
Can I ask why you don't consider with a fixed degree? Is it?
No, it's another space. Yeah, it's another reproducing kernel Hilbert space, but well, it's a different one. No. Yeah. So here, of course, that one will be almost trivial. No, it will be of dimension 2. Yeah. But in here, there's actually an interstick space. So to consider just these HLs, but I'm considering the sum up to some capital. So just to consider the space of polynomials restricted to something. So they have a different behavior, and the kernels are different, but both are interesting. But I will just be focusing on this one. Okay. Well, in fact, from the fact that this is a function on this geodesic distance, you can see that the kernel is rotation invariant. Okay? So if you rotate this x and y's, if you rotate both on the sphere, you get the same. Okay? And this is basically saying that the point process is what is called isotropic. Okay? So I mean, it's like if it's well, it's rotation invariant. Okay. And this is in fact telling you that this first intensity is constant, and you can actually compute the constant. No? The rho 1 will be just the evaluation of this kernel in the diagonal. Well, you can actually check that this is the dimension of the space. Well, this is just the normalization. Okay, so if x is x equals y, then this will cancel with this, and you get pi out. Okay. So for each realization, let's say of this point process, I will get pi L points. Okay. So in this particular case, for example, I'm having just the odd number of points. Okay, I get always 2L plus 1 points. Okay. It's, well, this is just when D is at least 2. Okay? If not, you get this station kernel actually. Okay. So this example here, and this is in fact already is known with another. It can be seen from another point of view. This is this circular unitary ensemble. This Q. Okay. Because so this circular unitary ensemble is this random point process given by the eigenvalues of random unitary matrices. Okay, so in the group of unitary matrices, you have this Haar measure. This is a probability measure. If you sample respect to this probability measure, and consider the corresponding eigenvalues, this will be random eigenvalues. Okay. These are random points, if you want, on the circle. And well, you can actually check that the process is exactly this. Okay, so this is the code. And well, as you can imagine, this is an object that you can define in much more generality because, well, in any smooth, compact Riemannian manifold without boundary, the Laplace-Trami operator is discrete, let's say, so it has a exactly this form. Okay, so you can define the space of eigenfunctions, yeah? Up to some given eigenvalue, if you want. Okay. And this sometimes are called the spaces of diffusion polynomials. Okay, so here you have a particular space of polynomials. So these are actually real polynomials. In a Riemannian manifold, these are no longer polynomials if you consider the span of eigenfunctions of the Laplace-Trami operator. In general, they are not polynomials, but well, sometimes they are called diffusion polynomials. And you can define exactly in the same way. Let's call it harmonic ensemble in so a point process at the end, because once you have the kernel, you can define the joint intensities, and then you will be able to define it in any Riemannian manifold somehow, well, maybe not intrinsic, but somehow related with the Riemannian structure point process that gives you points there that somehow are repulsive and somehow well distributed. We'll see in some sense, good sense. In the manifold.
So two things. One, for the Riemannian manifold, what will differ is the lambda L won't have that specific expression. The eigenvalues will change, but
yeah, this will change. Yeah,
but still you can.
Yeah, you have a yeah.
And the intensity in this case is a constant.
In this case, it's a constant. Yeah, but in general, so yeah, the manifold is ugly. Then it's not going to be constant. No.
Okay. Okay.
It will change with the point. It will be the kernel in the diagonal, but nothing else.
In this case, the kernel is constant on the diagonal.
I guess there are nice estimates for this object. So you have this Bail formula and all this to get information about the kernel in Riemannian manifold, but there's no closed expression in general.
So on the sphere, you have this decomposition and the harmonics.
Yeah.
So you have something similar on.
Well, you can define the space of eigenfunctions of a given eigenvalue.
Okay.
But in general, this is, well, the nice thing with the sphere is that this is a thick space. No, you have different so linear independence, more than one-dimensional space of eigenvectors of the same eigenvalue. And this is why this space is very nice. In general, they are going to be one-dimensional, or they are not so. But yeah, but you can consider the space up to some degree, and yeah, you will have a space of eigen. But yeah, you can also fix the eigenvalue and consider the corresponding of these HLs. But in fact, what as you have this degeneracy, actually, what some people is studying actually is what they call chromatic waves. So they consider just. So they group these eigen values. So if they are somehow close to something, so they pack them in blocks, and then you have a space with some more than one-dimensional space of to study. Okay, and in this sense, so they try to replicate the situation of the sphere, where for each eigenvalue you have a space with this HS space with more than one dimension. Yeah. But yeah, it's possible to define all these objects in general, and they will be interesting objects. Well, this is going to be one of the point processes that I'm going to study, these harmonic ensembles. But I will basically talk about things on the sphere. Okay? Yeah.
Is it also possible to extract the contribution from each of those harmonics in the sense of if I'm considering 0 to capital L, do I see that the later L's actually contribute a lot more to the fluctuations rather than as compared to the first few?
Maybe, I don't know. I don't know. Yeah, probably.
Because there is a similar picture in which you look at the band limited eigenfunctions.
Yeah.
Basically, you look at a fixed band, not fixed,
Yeah.
but a band, and then you keep shifting it, but also keep increasing the width size of the window.
Okay.
And then again, you will be in this scenario in which capital L, the size of the
And the contribution is basically from the
in certain for certain functions.
okay. Yeah, that would be interesting to check. Yeah. I don't know. But my next example is actually what you were mentioning. So I don't know. First, I will talk about the spherical ensemble. Well, this was already mentioned. So the spherical ensemble is this other process we saw. So this was considered way before, or well, independently of Mackey's contribution. But well, from the work of Krishnapur, actually, this point process. So when you consider independent random matrices with some given entries, random entries, and you consider the eigenvalues of this A minus 1B, then this is a determinant point process on the plane with respect to some measure. This measure actually. Well, I'm not going to go into the specifics of this, but again, so if you map this to the sphere, they somehow distribute nicely on the sphere. And in fact, if you consider this on the sphere, so you map the points to the stereographic projections, so z's will be in the plane, and now x and y's will be in the sphere. Then these kns are well, the norm of this is of this form. Okay? So in fact, you can see from here again that this second intensity is a radial function. This is going to be important afterwards. So it depends just on the distance. Well, this is the Euclidean. So this is the length of the segment, but I mean you can write also this in terms of the geodesic distance if you want. So it's a radial function. Okay? And again, as is stationary, this rho one, so the kernel diagonal is constant, and therefore, if you compute the spectrum number points respect to this point process, so if you consider
So Jordi, there is a eraser if you want to erase and write something else. So.
Yeah. Well, okay. Yeah, that's good. Well, if this so if xn is this spherical ensemble of the point process given in this form, then from here, for example, you can see that the expected number of points that fall in some subset C, subset oral subset, if you want, of the sphere S2 will be well, the integral of well, by definition is this. No? Is this with respect to the surface measure, and well, knowing this, well, this is just n times the measure of Z. Okay? So in this case, the expected number of points is proportional to the size of the set. Okay? So it's a very nice property. But well, the point is that you have this very nice spherical ensemble, and I will study this also. And finally, I will mention this other point process. I will handle this. The Bessel point process. So again, well, I will start basically with the
So the previous one you're saying is the D equal to 2 case of your this one or not?
Sorry?
The spherical ensemble.
Yeah.
And its relation to D equal to 2 of your first example. Are they related or?
Yeah, I mean, I just at the beginning
No, I don't mean that.
No, but I was meaning this. So the point was that I mentioned this spherical ensemble before.
Right. I mean, I'm asking your spherical harmonics based determinant process when D equal to 2.
Yeah.
Is it
to the harmonic ensemble? No.
It's not.
No. It's something different. So these are different processes. So you have this harmonic ensemble, and you have a different. In fact, in some senses, we are going to see much better process, and this will be the spherical ensemble. But the problem of the spherical ensemble is that it's just two-dimensional.
Yeah.
But in dimension 2, this is better than the harmonic ensemble in for example, distribution sense. And we'll see that there's a clear difference between these two. But yeah, the last example is basically this thing that was mentioned. So you have the space of you can consider the space of unlimited functions of finite energy. So it is called the Pauli-Wiener space. So this is the space of L2 functions in RD such that the support or the Fourier transform in distributional sense is in the ball. So this is the Pauli-Wiener of the ball, Pauli-Wiener space of the ball in RD. Well, these functions actually can be extended naturally to be seen as entire functions. Okay, can be extended. It's a space of functions in the space of, so it's a space of holomorphic functions, entire functions. Okay, and so these are. This everything is real, okay? But you can just consider. So once you have the Fourier transform, you can consider that the variable is complex, and then you have already an extension of this to a space of entire functions. Okay? And well, it turns out it's possible to see that actually this is a very natural space of functions because these are of exponential type. So if you consider a point, then this is bounded by you have a bound of this kind for the functions in the space. Okay, so if the function is in Pauli-Wiener space, then it grows exponentially. Okay? This is somehow natural because, well, if you think about it, so if it grows polynomially, it's a polynomial. Then the next thing if you consider the next order of growth after polynomial, well, it will be the first, will be kind of exponential. So this is the exponential growth. Okay? So once you have this space of unlimited functions, well, this is in fact a reproducing kernel Hilbert space. The reproducing kernel, in fact, can be given explicitly in terms of some Bessel function, and well, in fact, we are going. Well, of course, now these point processes are infinite dimensional. So before I was just mentioning, well, I have this finite number of points on the sphere, but now I have an infinite number of points in RD. Okay. But what I can do in order to get an increasing or a moving sequence of point processes is to change somehow the intensity. So the row one, let's say, expect the number of points that I will see in a subset. So I can increase this somehow, by rescaling. Okay, and in this sense, I will rescale the kernels, and this will change essentially this expression. And well, this process is somehow nice because well, it's for example, has been proved that this instance is in some sense universal. Okay, so if you have if you consider this previous harmonic ensemble point process on any compact running manifold, if you look this macroscopically, if you want, so you will get you will end up with this Bessel process. Yeah, so it's somehow related to the previous one. Okay, but well, in any case, for example, in D=1, this has been widely studied because this point process now is a so-called sign process that appears a lot in random matrices. And well, the referencing kernel of the polynomial space is just the cardinal sign, and this is exactly what you will get here. Okay, the cardinal sign. And if you look at realization of this, so this is a one-dimensional realization. I did this on our paper by the and well, if you get a window, if you consider a window of all RD, well, in this case R2, you will see this bunch of random points nicely distributed somehow. Okay. So, okay, I'm sorry, I have time, so let's move here.
You have 10 minutes.
10 minutes?
You have 10 minutes.
Oh. Yeah. Okay, then I'm sorry for you.
Also isotropic, right?
Sorry?
This point process is also isotropic.
Well, this will be a translation invariant.
Transition invariant.
Yeah. So you have translations now in RT, and then yeah, you have this nice property. Yeah, because again you have this radial, so it depends just on the distance. So this is a translation invariant. Okay, well, the expression is not really important, but it's somehow a natural. Well, there's another example, the Geneva process, but I think I'm going to skip this. You can read it if you want to read it in the slides. Anyway, so if I have 5 more minutes, then I will start with the, because now once we have all the objects in the definitions, all the notions on the title and some examples. Now the idea will be to try to convince you that actually it's interesting to study these fluctuations of linear statistics or determinantal point processes. Okay, and for this I will try to give a couple of things that are listed from my attention. So the first is to Monte Carlo integration. Okay, so I'm not going to really go into this, but so I will focus in the second motivation, let's say, but well, there's something called Monte Carlo integration where you actually choose random. In the most simple case, you get you consider uniform independent points, whatever, in some manifold, and you try to use those to integrate numerically. Okay, so this was somehow the simplest version of this Monte Carlo method, and. But of course, the way to recover the integral is through this, let's say, Riemann sums. As you can see, these are actually linear statistics. Okay? So if we want to say something about this, how these Riemann sums approximate the integral, that turns out to be the expected value of this linear statistic, then we can try to study fluctuations. Okay, so for example, well, in this uniform, so this is no longer determinantal. So here I'm considering ID uniform points distributed in a manifold, if you want, in the sphere. But in this particular case, well, you compute everything. So if you consider a function, the expected number of points is well, it's just the integral. So this is the object we want to somehow study, the integral, and how this guy here approximates this. Well, of course, I can assume some regularity because if not, it's not clear what does this mean as an approximate of the. But well, the point is that even in this level, you can compute the variance, and it turns out to be this. Okay, and well, the point is that if your goal is to control this this error, okay, well, you can easily get some rate of approximation just using IntelliJet. So you can bound this expectation by the variance, and you will get this. Okay, so this is like what it goes like the square root of n. Okay? Well, this is of course this method is good for because it's very simple and you can implement it easily. But the rate of approximation is not very good. Okay, of course. But well, in some cases is very useful. But then a natural idea here that this somehow, well, in fact, was one of the reasons why we started to work on this fluctuations is well, what happens if because well, the problem here is that again with this ID normal. ID uniform points, well, you have a lot of clumping and some empty space in the manifold. So, well, it's good somehow to integrate because it's easy to implement. But what happens if you consider something better, for example, this, and you try to integrate respect to these determinantal point processes? Okay, so it's a natural question. And this was actually addressed by these two people, Bardenet and Hardy. Well, the result now I'm not going to go into this, but so I have this until 30. Yeah, okay. But well, the main point is that they define another determinantal point process, and they end up with this this ratio of approximation. So a better one than well, as you may expect, if you have now some implemented repulsion between points and the points are nicely distributed or better distributed, then your approximation is going to be better. No? And well, the setting now is not really. So this is again a determinantal point process with respect to some kernel given by the Legendre polynomial. But well, the point is that you can approximate now with some improved ratio. You can apply Shosnikov central limit theorem, and you have basically the behavior of this approximation, somehow the limited behavior. And there's some something that is going to be important later. So that there's a bit here. It appears some explicit expression that involves somehow the regularity of the function. But well, the point is that you have this, and then a natural question will be. Because, well, the first thing, well, a few comments. Well, the first is that the key point in all this result basically is to compute this. Okay, they actually prove this. They a specific limit for the asymptotics of these fluctuations. Okay, so this, and once you have this, you can apply Shosnikov and you will get all the rest. Okay, so this is the whole point. And well, in some sense, I think this is somehow because well, of course, the problem is that these determinantal point processes, although there's a nice algorithm that you can actually implement, you can find in this book. So in fact, it's sometimes called this HKPV algorithm. So there's an algorithm to implement and to get points from a determinantal point process. But in general, is much more difficult and costly than uniform points, of course. Okay, but well, in some sense, this is well, this is something that is I think is interesting. So, but the net is saying somehow that that this because they have been studying now this determinantal point processes, so we can integrate using this quantum machines. No? And somehow he's saying that this is going to be, well, this is maybe too far-fetched, but the point is that, well, this may end up being somehow the paradigm of integration, numerical integration, because now it's very costly to get this point to integrate from a determinant point process, but in some sense, the idea behind this work that is very interesting. I invite you to check. So is that well, in a quantum computer, it's very easy to generate, let's say, fermions. Okay, we call that these point processes are called fermion processes, and they are basically immediately you can get some fermions using this quantum machines. So if this may at some point gets really end up actually working, so you can basically get points without cost. Yeah, so this is obviously really not realistic. But well, the point is that that there's some, and they have been studying this well, numerically, and the behavior of this determinant point processes as a way to integrate. Okay? But well, my interest is basically theoretical, say. So that now I would like to say well, to see what happens, for example, with other in other settings. So if this improved behavior of the integration is like this, and well, this is well, this is already known in other settings, but well, I will start with this. Thank you.
Any questions?
Yeah, so you mentioned that this is also related to theory.
Yeah, because well, in fact, this QA, this circular unitary ensemble, is somehow considered as a good approximation of the behaviors of the zeros of the zeta function, and in fact, if you take the zeros of the zeta function and you just get a segment of them and wrap them on the circle, they really look like points from this circular ensemble. So they seem to, so they look like random points. So this is deterministic, but using, so in fact, for example, things that have been done is there are some, or there were some conjectures about the behavior of the zeros of the zeta function, and considering this somehow linked, has not been proved, but is some, well, there are some results by Montgomery showing that the second intensity somehow, or the correlation of the zeros of the zeta function behave like the sine kernel actually. So you have some relations that have been established, but most of what has been done, I think, is to try to use the random setting to get some conjectures about the behavior of these zeros. So
the distribution of the zeros.
Yeah, for example, the moments. There's a famous work by Snape and Keating is Snape, yeah. And they were able to act. There were some coefficients that were unknown in the conjecture how these moments of the growth of the Riemann zeta function on the 1/2 line is, and they were actually able to relate this to the characteristic polynomials of the QE, and in that level they were actually able to compute the coefficients, and this is now the conjecture. And this conjecture matches the original work by Littlewood and Hardy, I think, and Ingman actually, because I think they were able to compute two moments. And but now they have this general conjecture where you have an expression for all the moments, and this is basically from this. And there are numerically, well, there are numerics that suggest that this is all somehow correct. But yeah, there's a lot of work on this. That's it.
Any other question?
The process you had just before that coordinate Hardy result.
Yeah.
Before the process. It was a tensor product of kernels, right?
Yeah, it's like a tensor version of the. Yeah, they consider this on the square. Yeah, and they consider like the. So the process given by. So this is actually the norm. So this is the reproducibility with respect to this legend polynomial, and then you tensorize this.
So that's also like a harmonic ensemble, is it?
Yeah.
They satisfy some second order difference. I don't know what they satisfy.
Probably it's yeah. Well, yeah, the legend satisfies some, and probably maybe there's some differential.
M here.
Sorry.
What is M here?
M. M is so you get n points, m to the t.
What is capital? Capital M is my choice.
Yeah, yeah. Yeah, you can choose the points on the interval, and then you get n points for the process. M is yeah. Sorry, the writing is not really clear, but yeah, you choose m, and then your process will have m to the d points.
That looks more like the harmonic ensemble, right? Where you had a L to the D was the number of points.
Yeah, well, in fact, yeah, but it's true that it's tensor. It's a tensor, yeah. So it's a really square thing, and.
Okay. Any other questions?